Okay, I want to start by thanking Enrico, David, and the organizers for the opportunity to speak to you. For the next half an hour or so, I want to talk about the subject of wave dark matter. And this is work done with a large number of collaborators. I won't have time to talk about the work contained in all these papers. Probably the first 10 minutes of the talk, the introduction part is largely from this first paper here. And the bulk of the talk would actually be from the fourth paper on vortices. And then a minor portion of the paper of the talk would be on the last two more recent papers, hopefully. And in case you're interested in more background, I've been working on a review that hopefully would be available on the archive in a week or two. So let me step forward. I don't think I need this introductory slide at all. We know we have a lot of evidence for dark matter. Yet we are very ignorant about its very basic properties. For example, the mass of the constituents. And here on this scale, I just illustrate our degree of ignorance by just pointing out there's a huge range in mass, all the way from what I would call in this talk ultralight, 10 to the minus 22 electron volts, to basically solar mass or tens of solar mass, astronomical objects. On this very vast spectrum, there is one interesting scale that we can actually put down, and is based on the following observation. We do know the mass density of dark matter in the solar neighborhood, for example, and it's from basically motion of stars. And it's about this number, 0.3 GeV per centimeter cube. And we can ask the following question. At what dark matter mass, particle mass, would the interparticle separation be less than the corresponding de Broglie wavelength? The de Broglie wavelength, of course, depends on velocity. It's 1 over mv, or 1 over momentum. And here by velocity, I'm going to take it to be the velocity dispersion in the Milky Way, which is about 200 kilometers per second. And it's a question we can ask now, given the observed dark matter mass density, at what mass would this inequality hold? It turns out to be given by this scale, around 30 electron volts. So for mass less than 30 electron volts, we will be in this regime, and it's illustrated in this little cartoon at the bottom. So imagine I draw a sphere, and the sphere has the size of the Broglie wavelength. We are considering in this talk a regime where the sphere contains many particles. In other words, these particles have to be bosonic, because the exclusion principle would not allow this to happen. And this is what I'm going to call the wave regime. It's fairly analogous to what we are very familiar with in ENM. We know if you have a state with many photons, generally, you can describe what is going on with classical electromagnetic waves or electromagnetic fields. And basically, it's the same regime we are considering here. We are interested in a regime where there's high occupancy, many particles per de Broglie volume. And associated with this, there's a lot of interesting wave phenomenology, basically. And I want to emphasize these are just classical waves. And to give you a sense of scale, I give you several different possibilities, right? So the ultralight, often called fuzzy dark matter, by the way, 10 to the minus 22 electron volts. But the Broglie wavelength would be truly astronomical. It's a sizable fraction of a galaxy. But in this talk, we are fairly open-minded. The mass can be, for example, 10 to the minus 6 electron volts is actually the target mass of some QCD axion detection experiments. The associated de Broglie wavelength, just to give you a sense, is some fraction of a kilometer. It's not astronomical, but it's still sufficiently large that is actually the wave phenomenology is actually relevant for detection experiments. So I hope I'll have time to talk about that as well. Okay, so keep these numbers in mind. So this is a rough outline of what I'm going to talk about next. I want to spend maybe 5–10 minutes talking a little bit about motivations. Why do we want to consider wave dark matter of this sort? In other words, a boson that is lighter than about 30 electron volts. And the bulk of the talk will be on the wave dynamics and the phenomenology, in particular vortices. And then I want to close with some remarks about astrophysical implications, which are mostly relevant if the dark matter is actually ultralight. And some remarks about experimental detection, which is relevant if the dark matter mass is not quite ultralight, but still in the wave regime. Okay, so let me start with the particle physics motivation. And here in this talk, I'm going to focus on a spin zero particle, a scalar particle, although a lot of the wave phenomenology would apply even if this is spin one, for example. A natural candidate for a light particle would be a pseudo-Nambu-Goldstone boson. If it were exactly a Nambu-Goldstone boson, it would be massless. And to remind you, I put in this picture, Mexican hat potential. The Goldstone boson is the one associated with the angular degree of freedom. If the Mexican potential is slightly tilted, then there would be a mass associated with the angular degree of freedom, hence the name pseudo Goldstone boson. A familiar example, perhaps the most well-motivated example, is the QCD axion. Unfortunately, due to lack of time, I won't be able to discuss what problem we solve. It solves the strong CP problem, as you probably know. There are other examples of this sort, often called axion-like particles, for example, in string theory. And in that case, the axion-like particles, which I'll just call them axions, they come from 0 mode or Kaluza-Klein modes of higher form fields when you have compactified extra dimensions. And there are many such examples in string theory. I do want to give kind of a footnote remark on particularly the ultralight version of this, why it's interesting, and it's interesting from thinking about the cosmic abundance, the leftover abundance from the Big Bang. So let me just spend a few minutes on that version. And by ultralight, again, I mean something around this order, but you will see in a moment there's actually a pretty large range. The scalar field we have in mind is phi, and remember this picture, phi is some angular field. And as an angular field, there is a mass scale, which is the periodicity scale, which I'm going to call F here, is often referred to as the axion decay constant. Again, if this were a true Goldstone boson, then there should be no potential. This term should not be there. However, very often non-perturbative effects would generate a potential suppressed by some instanton action. And we are going to have in mind an instanton action that's moderately large, so that this is a small breaking of the shift symmetry if you want. So this lambda, this mass scale, this energy scale is somewhat small. The periodicity is preserved, so that hence this cosine form. And if you expand out this potential and read off the quadratic term, the m squared phi squared term, it tells you the mass, which is related to this combination of lambda, which is this coefficient in front, and the periodicity scale, or the axion decay constant. And again, there are many such examples. The QCD axion, by the way, does not have this exact potential, but the story is rather similar. As you will see in a moment, the lambda that we have in mind is very small, much smaller than the QCD scale. And so this version, the ultralight version, that axion is not the QCD axion. Yet there's an interesting story associated with that, which I want to tell you here. If you think about what is the radic abundance today, you want to start in the early universe where this scalar field, this axion, or axion light particle, it has, this field has some primordial value in the early universe, and for lack of a more well-motivated assumption, we are just going to assume it's of the order of the scale in the problem, which is the axion decay constant. In other words, we say this is some primordial misalignment. The misalignment angle is order 1. Phi over f is order 1. And because of Hubble friction, this scalar field will just be stuck at this value until when the Hubble expansion rate drops to of the order of the mass scale of the particle, which is basically the curvature scale of the potential. This scalar field will start rolling down the potential and commence oscillations around the minimum. And you can interpret this oscillation as basically a set of particles. As the universe expands, in fact, the Hubble friction would cause the oscillation amplitude to redshift. Eventually, you can just forget about this whole cosine shape of the full potential. You can just focus on m squared phi squared close to the minimum. And you can show fairly easily the energy density in this oscillation redshift like 1 over the scale factor cube. So it behaves like matter, non-relativistic matter. And if you follow the story, which I'm skipping, but it's not too hard to show, the radic abundance today, omega, in basically this dark matter, is of the order of what you would want to account for the observed dark matter abundance if you make 2 assumptions. One assumption is the axion decay constant is somewhat close to Planck scale, somewhere between Guth scale and Planck scale. Seems to be a fairly natural number in a lot of string theory constructions. And if the mass is actually close to this ultralight value, 10 to the minus 22. If you like, this is one motivation for thinking about a fairly light particle, that in this misalignment mechanism story, you fairly straightforwardly get the right cosmic abundance for that matter if the mass is fairly light. However, I should say the abundance is more sensitive to your choice of the axion decay constant equals like f squared, and less sensitive to the mass, right, n to the 1/2. So in fact, since we are fairly ignorant about what actually f should be, there really should be a fairly large range for n. So keep that in mind. Nonetheless, we take this as a hint that perhaps it's useful to think about dark matter, wave dark matter, and even wave dark matter whose the Broglie wavelength is actually astronomical in size, which is often called fuzzy dark matter. Okay, so that is my motivation. Let me now go ahead to describe the dynamics. The dynamics is actually very simple. As we discussed before, let me just skip back for a moment. You have oscillation fairly close to the minimum, so you have just basically an m squared phi squared potential. And so the equation is the good old Klein-Gordon equation that describes the dynamics of your scalar. We are interested for structure formation. We are interested in the non-relativistic regime. Recall in the Milky Way, the particles do not move at high speed, right? It's 200 kilometers per second. It is a fairly useful thing to decompose your real scalar, the axion, in terms of basically a complex scalar psi. You factor out the primary time dependence, which is the oscillation with frequency m, as you can see in the Klein-Gordon equation. And this psi is a complex scalar, and you add the complex conjugate to make phi real. And the assumption, the non-relativistic assumption you can show is the same as the following. You say any time derivative on psi is small compared to the time scale given by m, basically. In other words, psi is slowly varying compared to m, the time scale associated with m. And in that case, the Klein-Gordon equation reduces the Schrödinger equation. And for this talk, the only interaction, maybe until we talk about direct detection. The only interaction we are looking at now is gravitational. So that's why there's a gravitational potential here. This is the gravitational potential. And this is basically the only equation we need to know, in addition to just one more. The other equation is Poisson equation. So the gravitational potential, capital phi, is sourced by the density in these dark matter particles, which is just given by the rest mass m times psi square. And that's it. These are the only two equations we need to study the dynamics. And it turns out it's a very rich dynamics. One remark I want to make, just to emphasize a point I made earlier, even though we have a Schrödinger equation, and I'm going to refer to this side as the wave function, as usual, what we are describing here is really a classical system. So think of psi as a classical wave, even though it looks like the quantum mechanical wave function. An alternative point of view, which is useful, which I will refer to in a moment, is to think of this as a fluid. As a fluid, you can think of it as follows. The fluid density is naturally basically psi square, right? So rho, the mass density is m times psi square. Psi is a complex scalar field, and so there is a phase. And it turns out what you want to do is to associate the phase as with the velocity potential. In other words, the fluid velocity goes like the gradient of the phase. Expressed as such, mass conservation immediately follows, and this is just another way of expressing something that might be more familiar. Recall in Schrödinger equation, there is a conservation law associated with the U1 symmetry of psi. And in quantum mechanics, we would call that probability conservation. In this context, in this fluid interpretation, we recast it as mass conservation. Now, the Schrödinger equation is a complex equation, so there really should be two independent equations. One is mass conservation, the other turns out to be Euler equation, and it's written in this form. Most of the terms look very familiar. The fact that there is this term on the right just tells you the gradient of the gravitational potential supply acceleration to your fluid element. This is the acceleration. The second term on the right is maybe a little bit unfamiliar looking. In the literature, it's often called quantum pressure. For our purpose, it's a little bit of a misnomer, because one, we are talking about a classical system, and two, actually is not actually pressure. In fact, it comes from some form of stress. If you work out the stress tensor for this scalar field, it has off-diagonal components. And it's that particular structure that actually gives rise to this term. Okay. Nonetheless, it behaves somewhat like pressure. There's some gradient acting on, in fact, this has actually high gradients, 3 gradients acting on some combination of density. This way of writing is also helpful from another point of view. If you take the large m limit so that this term is negligible, you can see this pair of equation is what we often use in large-scale structure that describe basically conventional cold dark matter where pressure is negligible. So the large mass limit basically reduced to conventional cold dark matter. And just one more remark, the fact that the velocity is pure gradient flow is going to be important to us later. And from that point of view, you can think of this as some sort of superfluid. Okay, I'm going to skip the next slide and I'm going to move to the kind of the phenomenology. So the dynamics, again, is described by a Schrödinger equation plus Poisson equation. That's it, very simple. What are the wave effects that I'm talking about? And it can be actually seen in just this very simple picture. What is this picture? This picture is a snapshot from a cosmological simulation. So you start with the usual Gaussian initial conditions. You solve those two equations and just let it evolve forward, assuming small fluctuations in the early universe. What is very interesting is once you evolve to the nonlinear regime, in the late universe, you see this ubiquitous wave interference pattern, basically. This is wave interference pattern along the filaments. These are probably two collapsed halos or collapsing halos. And you can see these interference fringes. And it's an inevitable consequence of having dark matter as waves. So think of, for example, a halo like this as composing, not as a set of particles, but composing a set of waves. And these waves as random phases. And so they would interfere, sometimes constructively, sometimes destructively. And so you should always see this kind of interference pattern. The typical separation, the fringe size is the de Broglie wavelength itself. And this kind of picture was first observed in these nice simulations by Shai, Chiu, and Broadhurst. And later it has been confirmed by many groups by now. And again, it just comes from solving those two equations, Schrödinger equation and Poisson equation. Okay. And I think I'm going to skip this movie, and I'm going to now talk about some interesting kind of implications of these wave interference effects. There are actually many. I'm going to focus on something that's more recent that we have done, starting with the subject of vortices. Let me check the time. Okay. Maybe I will have time to talk a little bit about the scattering of tidal streams and soliton oscillations. They are all actually related to this wave interference phenomenon. I don't think I'll have time to talk about the basically accretion of dark matter onto black holes or the subject of black hole hair. So let me start with vortices. Your first reaction might be, why are we even talking about vortices? Because you might recall in the fluid interpretation, the velocity is pure gradient flow. And so the curl velocity is by definition 0. So there should be no vorticity. So what am I talking about? There is one loophole in this actually fluid interpretation. And the loophole is actually precisely places where rho is 0. If you look at the wave function, it's clear at places where rho is 0, the phase is ill-defined. And so in some sense, this fluid interpretation actually breaks down in those places. What are these places where rho is 0? Well, these are precisely the places where you have complete destructive interference. Again, just by random chance, you have these waves sloshing around in the halo. They interfere. There will be places where the destructive interference is complete. The density is actually 0. One might think this is actually very rare. In a moment, I'm going to show you. In fact, it's not rare at all. It occurs actually fairly frequently. We can even quantify how frequently. Suffice to say, if such places actually exist, where the density is 0, you have to think about basically what happens to the fluid flow, the velocity, around these places. And it turns out, as I'll show in the next slide, the velocity inevitably actually circulate around these places. So it's some form of a vortex, as you will see. Before I describe that argument, though, I want to emphasize, and it's important to emphasize this. This kind of complete destructive interference that can form a vortex can only happen in the late universe as a result of gravity. Why do I say that? Remember, in the early universe, the universe is mostly homogeneous. So this scalar field psi is more or less homogeneous everywhere, with small fluctuations 10 to the minus 5, which means even though these waves can interfere, they can never take the density or the wave function all the way to 0. That's impossible because the fluctuations are so small, 10 to the minus 5. You have to wait until gravity does its work, amplify the fluctuations to become order 1 or larger. For example, around galaxy halos or inside galaxy halos. Now, in those places, complete destructive interference can now actually happen, and you can have a formation of what I will explain as vortices. I should say the phenomenon of vortices in superfluid is fairly well understood in condensed matter physics. So much of what I have to say is actually known. The only novelty I would say in this case is these vortices actually form from basically the action of gravity. Okay, so what is the argument? Let me start actually with the first bullet point. This is the only detailed argument I'm going to give in this talk. Hopefully you will bear with me. I'll spend a little bit of time on it. Enrico, can you remind me how much time do I have?
Sorry, can you hear me? Yes.
Yeah.
So I have you ending at 16:35. So that would be 20 minutes.
Okay, fantastic. Thank you, Enrico. Okay, so I have some time to explain this. I want to go over this in a little bit detail. So we are interested in having three.
Sorry, I just realized what I said is the end of this of the session, but
Yes.
you're supposed to end 10 minutes before that, so we can have some time for questions. So sorry, I should have said that you should end in 10 minutes, so then there are 10 minutes for questions. That's
fantastic.
The correct one. Sorry.
No problem. Yeah, good. So we are interested in what happens in three spatial dimensions, and let's ask ourselves the following question: what are the set of points where the density or the wave function vanishes? And remember, we want both the real and the imaginary part of the wave function vanishes. Now, if you ask what is the set of points where generically the real part vanishes, you describe a surface if you think about it. And likewise for the imaginary part, you'll be another surface. Where the two surfaces cross would basically be a line. It's a one-dimensional object. In other words, we are interested in something like a line or a string defect. So I draw that here with this purple line here. Imagine this is the line where generically, again, just by random chance, destructive interference is complete. Here, the wave function vanishes. Let's ask about the phase of the wave function as you go around the line, yeah? And if you go around, because the wave function has to be single value, it's clear that the wave function must wrap, basically must wind by integers of 2 pi, and it's an integer. And if you recall how the velocity of the fluid is related to the gradient of the phase, it basically tells you the velocity integrated around a loop must also have this kind of integer winding. In fact, you can actually say a little bit more. If you do a Taylor expansion, which is what I want to describe here, imagine x equals 0 is where the wave function vanishes. It's 1 point on the vortex line. And if you do a Taylor expansion, then assuming the first gradient doesn't vanish, this is the dominant term in the neighborhood of that point, right? And therefore, you have a fairly generic prediction. The density, which is psi square, must go like the separation to the vortex square. So rho goes like r square, okay? Moreover, the velocity must drop like 1 over r, again, just from this equation, because the size of the loop clearly goes like the separation. And since this is independent of separation, the velocity must drop like 1 over r. These are fairly generic predictions. And as you can imagine, these are useful for deriving observational consequences. These are generic predictions for vortices. Let me say one more thing. These vortices generically take the form of a loop because these vortex lines, they are like magnetic fields. They cannot end. So in general, they close upon themselves. So it's really like a vortex ring. And for those of you who are familiar with axion string, I want to emphasize these are not axion strings. For the QCD axion strings, for example, the U1 associated with that is the Petri-Quinn U1. The U1 associated with this line defect, this vortices, is just the U1 associated with particle number conservation in the non-relativistic regime. It's the same U1 of the Schrödinger equation. Okay, very good. Now, once one have this understanding, we can actually look for these things in an actual simulation, a cosmological simulation. Can we find these things? Do they have these properties that we predict? And how often does it happen? So in the brief remaining time, I'm going to skip a few slides. So this is, for example, one halo. You cannot actually see the halo, but we highlight basically the vortex rings inside the halo. You can find them. The way you check these are true vortex rings, by the way, is to check the phase. That the phase, if you go around, that's rep. And this look nice because this is spherically symmetric halo, but in fact, more realistic halo, the vortex rings looks more messy. You can check the density profile around the rings. It goes like R square, as we discussed. You can check the velocity profile, drops like 1/r. So these things all check out. I'm going to skip these solutions. These vortex rings actually can have very interesting bulk motion. This is the vortex circulation around this ring. In addition, the ring as a whole actually would move through the fluid with a velocity that goes like 1 over the radius of the ring. And I'm going to skip this movie and skip this slide also. Let me make a few comments about these vortex rings. Number one, which is probably the question that naturally comes to mind. Are these rare? The answer is no, they are not rare. In fact, you can show you should expect roughly 1 vortex ring per de Broglie body. I already go over the movement of the rings. Let me emphasize these vortices are transient phenomena. These vortices actually evolve with time, they change. The time scale is basically the de Broglie time, which can be very long if the mass is very light, ultralight. Due to the lack of time, I think my time is up. So I'm going to just very quickly talk about some observational consequences, right? Let me skip this slide. For the ultralight version, the observational consequences, probably one way to look for these things is through gravitational lensing. In cases where you have strong lensing, where you have images that are highly magnified, in other words, they are very close to the critical line, you can find what people call lensing anomaly, which means the magnification actually differ. And it's basically due to substructure, this interference substructure. So that's one phenomenon that one could look for. The other phenomenon is basically tidal streams. People see tidal streams from globular clusters inside the Milky Way. And those streams are very nice, thin, and cold. But over time, they can be scattered by these interference blobs or vortices and creating fluctuations that you can observe. So this is something that we recently looked at. In this paper, I'm unfortunately out of time. I want to say something about experimental implication, which is also kind of fun. Imagine the wave diameter is not ultralight, but just light. So something like the QCD axion, 10 to the minus 6 electron volts. There are a lot of experiments that attempt to detect it. And of course, to detect it, you have to go beyond gravitational interaction. These are the two interactions that people generally focus on. One is coupling of phi to FF duo of the photon. The other coupling of phi is a derivative interactions to fermions. One could think of it as coupling to the spin of the fermions. And there are many experiments. Essentially, they measure different combination of phi. Phi spatial gradient. The spatial gradient basically causes the spin to precess, or time gradients. What I want to emphasize, this wave picture actually tells you that there is one interesting way to think about this experiment, and it goes as follows. Recall the axion field is basically the wave function times this fast oscillation. So at any given location in space where your detector is, this, the axion field probably has this kind of time profile. It has fast oscillation. This is the oscillation time scale 1/m. But it has longer time scale modulation, which is the de Broglie time. And axion detection experiments are actually sensitive to both time scale. And the fact that you have waves with random phases means basically this modulation is stochastic. And the best way to think about your experiment is really, you should think of it as a measurement of correlation functions. For example, you can think about measuring 2-point correlation functions in time or phi. You can even think about measuring space-time correlation functions. At vortices, if you have vortices, remember vortices actually have occur at the rate of 1 per de Broglie volume. So they are actually fairly generic. If they pass through your detector, phi is 0, as we said, the wave function is 0, but the gradient is not, which means some experiment would not see 0, but some would. Furthermore, perhaps most interesting is the following. Having vortices tells you basically your axion must oscillate with a phase that has interesting winding structure. And perhaps that could be exploited to enhance the probability of detection. It's something that's we're exploring. And I think I'm going to close. Unfortunately, I don't have time to talk about these other interesting phenomenon. Soliton oscillations have to do with wave interference as well, which is a density oscillation in the middle of a halo. And let me close, right? So the main point I want to get across is the following. If we have a dark matter particle, necessarily a bosonic particle lighter than about 30 electron volts, there is generic wave interference phenomenon. They are unavoidable, and vortices, if you want, is one manifestation. There are actually many manifestations. And one could look for these wave interference phenomenon in both the astrophysics observations and also in direct detection experiments. And I'm going to end here. Thank you for your attention.
Thank you very much, Lam, for this nice and clear talk. Good, yeah, we have a few minutes for questions. I see Spiros has a question.
All right, thanks a lot for the talk. Could you comment a bit on the stability of these vortex solutions? Because I think that in 3 dimensions, it's hard to get stable solutions, right?
Good. They are transient in the following sense. So if you have, let's say you have a vortex ring, inside a halo, the vortex ring could, for example, they can collide with other rings. They will evolve in size and so on. However, once you have a vortex ring present, they cannot just arbitrarily disappear. And the only way they can disappear is for the vortex ring, for example, to shrink to 0 size, and then it can be gone. So I would say they are not absolutely stable, but they do have some integrity to it. Meaning once you nucleate a vortex ring from 0 size and they grow to finite size, it will stick around for a while, and you can actually predict roughly on average how long it will stick around, which is the Broglie time, the Broglie wavelength divided by typical velocity. But you're right, in general, they can also disappear, but the only way they can disappear is to shrink to 0 size and then be gone. Yeah.
Okay, good, thank you.
Fernando has a question.
Okay, thank you. Well, it was a very nice talk, thank you. How much of your discussion depended on the fact that the particle is a pseudoscalar rather than a scalar?
A very good question. Not really, not very much. The wave interference aspect doesn't really depend on whether it's a scalar or pseudoscalar. The vortex aspect also does not depend on that. The only part of the talk where I actually make the pseudoscalar assumption is where I talk about direct detection. I only show, you know, phi coupled to FF dual and this derivative interaction to fermion with the gamma 5. So that's the only place where I assume it. If it's a scalar, of course, then there are more possibilities for direct detection, more interactions, as you know. But yeah, most of the talk, it doesn't really matter.
Perfect. Thank you very much.
Thanks for asking.
I actually have a quick question myself. I think it's going to be pretty trivial, but just to understand the bigger picture, of course, we have evidence for dark matter also on larger scales, in particular from the CMB.
Yes.
So now it seems to me that on large scales, you can always describe this using some kind of EFT of large scale structure.
Yeah.
For example, because that does include in the stress energy tensors arbitrary terms that are expanded in derivatives of density
Nice.
and velocity, and yours is just a particular cubic derivative with some square root.
Yes.
So my understanding is, but please correct me if I'm wrong, that on larger scales, this is indistinguishable from some kind of EFT approach. But then the big difference is that you claim that as I go into the nonlinear regime, all the other terms that could arise actually don't arise, except for d Laplacian square root of rho over square root of rho, something like that.
Very nice, very nice. You're exactly right. So if I stay above the de Broglie scale, then this wave, this wave phenomenon, basically you can ignore them. And really, this is basically the same as conventional cold-dark matter, which, as you know, you can describe by basically the usual, basically EFT description of large-scale structure. If you want, this is one particular UV completion of the usual EFT of large-scale structure. It's one particular UV description completion that is, for example, appropriate for the axion. Yeah.
Yeah, that totally makes sense. Yeah, you can resum all of those derivatives into a theory, and that actually you get waves rather than things that die before they can oscillate once. Okay, yeah, that's clear. Cora, you have a question?
Hi, Lam. Thanks for the nice talk. So I was wondering, since you thought about wave interference, let's assume we add some baryons to the mix, right? And we basically have some wave-like dark matter. What happens if we add baryons? Can we still really see those interference patterns?
That's a great question. And now, of course, the baryons, they are not wave-like, they are like particles. So the dark matter are wave-like. In the mix, there are other things that are actually more like particles, like baryons, for example, or stars and so on. The wave phenomenon will still be there, meaning if I look inside the Milky Way halo, presumably, unfortunately, it's hard to actually see the dark matter directly, but if we are able to see it, presumably this interference, basically the Broglie-sized blobs and vortices, they are there. Of course, they interact with the baryons gravitationally, so there would be some non-trivial interaction between them. In particular, there would be one thing that I think is worth thinking about. There has not been a lot of work on this, but I think it's interesting. For example, the quantum pressure, if you want, basically prevent the dark matter to become very inhomogeneous on scale smaller than the de Broglie wavelength. The baryons has no problem doing that, right? They can cool and collapse and form very dense objects, much smaller than the de Broglie wavelength. So it would be a mixture of basically, on small scales, you have basically high density baryons, and with this basically the Broglie sized blobs in the background, and they interact gravitationally. And it's actually fairly interesting to think about objects that you might form because of these interactions. The fact that the dark matter has difficulty collapsing into very dense stuff, whereas the baryons can, again, because of quantum pressure. Yeah, it's a great question. There has not been a lot of work actually exploring this.
Okay, thanks a lot. So thank you again, Lam, for the nice talk. And